Okay, so today I'm going to cover the topic of mesh generation, or how to generate a lot of connected elements. So as you have been seeing, the first assignment here, you did the mesh yourself. You kind of stitch it together using the topology and coordinates. But when you have a large problem, this is not feasible. You need to have resolution, have enough elements to kind of, for the numerical solution to be valid. So for larger complex problems, you need to create these meshes using algorithms. And there are many algorithms that you can use that takes a geometric description as input. So lines, curves, surfaces. And in this geometrical description, you can also add area and volume limitations. So for example, I can tell the mesh generation algorithm that I need to have the elements can only be as certain size. They can't be larger. You can also tell the algorithm how many elements there should be on the line. Or you can also refine the mesh by taking the results from a previous calculation and refining the mesh to increase the number of elements. That's when you have a high gradient, for example. We will not be doing those fancy stuff, but it's possible with this many of the mesh generation tools. There are two major types of mesh generation. So there is something called structured mesh generation, where you have a rule that defines the mesh. Typically, you specify, for example, you have rows and columns, and from that you can create a mesh that has certain number of elements in a row and certain number in columns, and that can also be extended to 3D rows, columns, and also in the depth. Some people prefer the structured mesh because you have a lot more control, but sometimes the geometry is complicated and it's not possible to create a structured mesh for very complicated geometry. You can do it, but it requires you to divide the area in smaller parts. So there is a second type of mesh generation, it's unstructured mesh generation. And that is an algorithm that takes the geometry and basically fills the area with elements. Often there is a limitation on triangles or tetrahedral elements, but you can often get through or create 4-node and higher elements by merging triangles and tetrahedral elements, so you can avoid this limitation. So how can it do? So this is an example of an unstructured mesh. It's kind of characterized that we have this kind of random points everywhere, and they're connected together by triangles. And here you can also see there's a wing. There are elements around the wing, and you also have refined the mesh around the wing like this. And this is also a unstructured mesh or half circle. Structured meshes have a more regular appearance. So usually you can define, here you have rows of elements here in a certain rule. You can have different distances between them. But you can also have elements with structured elements that have curves on the sides. So you can have bent elements like this. But the thing is that you have a rule that determines how many elements there are per side, and also how dense they are on each curve. As I said before, you can create quite complicated geometries using structured meshes, but you have to kind of divide your area into subdomains. So here you have like super elements here. You have 4 sides, 1, 2, 3, 4. But you have a curve on one side, and then you can specify the number of elements on this side and on this side here. And then you can put them together. When they share geometry, they have the same number of elements on each side. And then you can kind of build, using these Lego blocks, quite complicated structured mesh. So this is this is symmetry. This is a tunnel segment here with different materials and different super elements like this. We are going to use a mesh generator called GMSH. It's a very common software in finite element codes. it can generate any kind of mesh from 1D, 2D, 3D. It also contains a pre and post processor. So if you open your Anaconda prompt and type GMSH, you will get the user interface where you can open meshes and you can edit meshes. It's quite complicated, and we are not going to use it in that way. We are going to send an input file to it, and it will generate elements for us. And it can do both structured and unstructured meshes. And you describe your input as a geometry with lines, circles, splines, surfaces, and so on. And geometry is usually defined in a special language where you describe your geometry. CALFEM will automatically do this step for you. So you will describe your geometry in CALFEM commands. And from those commands, you can generate this file that Gmesh requires to generate the mesh. So as I said, CALFEM uses Gmesh as the underlying mesh generator. And the mesh generation is implemented in two modules. You have the CALFEM geometry module for defining geometry, and you have a CALFEM mesh module for creating the actual mesh, or the mesh generators defined in this module. And you define the geometry using an object, a geometry object. So the first thing what you do in a code is to create this geometry object. And you can see it as a container for the geometry. And you pass that along to the mesh generator, which takes that object, looks at it, and generates a mesh. And the result from the mesh is the normal matrices that you have in CALFEM, like ADOF, chord, and so on. And as I said, the output from that can be used directly to in your for loops for assembling the system. So this gives you the possibility to actually generate quite large meshes in CALFEM and study more interesting problem than just 4 elements. So how do you define a mesh? So this is we're using a groundwater problem here. So we have a domain here in the blue, and there is something going down here, for example, blocking the water flow. And we define this by defining nodes here. So 0, 1, 2, 3, 4, 5, 6, 7. So we have 8 nodes. And then we define lines between these nodes. And we're also going to use parameters here. So we are not going to exactly specify the height here in values, but we will define variables so that we make a parametric geometry. So it will be very easy to, for example, change the thickness here by looping and create a new geometry and a new mesh. This is a very common problem in finite element, that you want to study what happens if I make this deeper or wider. How does it affect the flow, for example? So the first step we do is we need to import a little bit more modules than before. So we import the geometry here to be able to define geometry, and I prefix it with CFG for calfem.geometry, and we import calfem.mesh as CFM. Here we import calfem this, I think in your example it should be this underscore MPL as CFV. And then we import some utility function here using CFU. And then of course we have NumPy. As this will be a parametric problem, we will define some parameters here. So we make the entire problem 100 meters, the height 10 meters, and the thickness of this spot that's going down here will be 1.0. And then we'll define height as the depth here as height divided by 2. We can of course change this any way we like. We define some parameter properties, and then we start by creating a geometry object. So this is a geometry, it's a class, and the first statement here, we will create an object, a geometry object. So you can see this as a database, and it has several methods to define our geometry. So to create a point, we just call g.point and specify the coordinates here, 0 by 0 here. And then we just continue like this to define our entire geometry. And you can see here I use variables here to define the coordinates here. That means that we can easily change the geometry later on. We don't have to go into this definition here. We can just change the W, T, and H and D outside. Then we have to create our lines. And we use something called a spline here, even if it's use the same commander to create lines between 3 points or 2 points. So it's called spline, and then we just specify the topology here. And Gmesh uses zero-based topology, so it starts from 0. So the first point is 0, and then goes 1, 1 to 2, 2 to 3, and so on. And here is also something we need to define. We need to define boundary conditions. So we will have on this groundwater problem, we have one pressure on the left side and one pressure on the right side. And these are defined by this line number 2 and line number 6. So we go back here. So we have 2 and 6 here. Those we will apply a boundary condition on. So we need to be able to set a marker on those. So here the marker can be any number. You can also set define them as variables and put them here in, but it should be a number, any number. So I call this 80 and this 90. And we can use those markers later on in the code to retrieve the degrees of freedom, for example, at the line. So these markers are a way of getting back to the geometry in some sense. Because when you get a mesh, you have just coordinates and you have the topology of the elements. And we need to know on which coordinates we have our boundary conditions. And then finally, we need to tie all these things together to a surface. And we just tie them together here by specifying all our lines here. That will be our surface. If you don't do this, you will not get the mesh. You will get the mesh, but it's only a one-dimensional mesh on the lines. So surface makes sure that we get a mesh over to the elements. Yeah, that was what I said. This next step, we need to call our mesh generator. So we specify here the element types here. I think this is a 4-node element. We'll see. As this is a groundwater problem, we only have 1 degree of freedom per node. So we don't have a displacement here, we have a flow. And then we need to create a mesh generator. So this is a class, GMSH. And when we create this class, we give it the geometry as input. So here you can see the benefits of having objects that you can pass them along, that they contain a lot more information that you can pass along. You will use that in your own code later on as well. We set some properties here. So meshgen.L size factor 1. That means the elements can't be larger than 1.0 square meters or whatever unit you have. We specify the element type, the dots per node, like this. Now we are ready. Now we have defined every aspect of the mesh generation, and now we can call the create method here. And it has several output parameters, so you get the coordinates for your elements, the element degrees of freedom, so the topology. DOFs is an array of degrees of freedom for each node in the mesh. Boundary DOFs is a special dictionary containing the markers. So here you can go in. So there is a marker number and corresponding degrees of freedom for that marker. And then you also have element markers for same thing as boundary DOFs here. So it's for elements instead. And now we have everything we need to actually solve our problem. So now we can create our element matrices. So we start by calculating the number of degrees of freedom we have. So we just check the size of this one here. we create our element coordinate arrays using chord extract command. Takes edof, chords, and dofs as input. And then we can create our element stiffness matrix. And then we can do then we have to assemble here, and we do the same procedure as we did for the smaller problem here. We can now loop our edof, ex, and ey. In this case here, I use a 4-node flow element. And I pass ALX, ELY, and EP. We have the same element property on the entire area, and then we have D here for material matrix. And then we assemble it together. So now we also have specified boundary conditions and loads. We create our load vector here, LT zeros and dofs, 1. We create one array. So this is a bit different from MATLAB CALFem. So we have 2 arrays for specifying the boundary conditions. One defining which boundary conditions that are prescribed, and one array containing the actual values that are prescribed. And then we can use a command called CFU apply boundary condition. We put in BDOFs here, BC, BCval, and then the marker number 80. And here we have 0 pressure. And then we have boundary conditions here, BCval 90, we have 10 here. And that will update these variables. So when these commands are applied, these will contain the prescribed degrees of freedom that we have used. And then we can solve the problem. And then we can extract element displacements. And then we loop over here to actually calculate our element forces. We do some calculation here on the maximum flow. So we can know that. So, and then we have some visualization commands here. So draw geometry, draw element values, draw mesh, draw nodal values, set the color bar, and then we display all these windows. So this is the geometry we created. And the nodal values. So you can see here you have 0 is blue, and we have 10 here on the other side. And then you can see the differences in pressure around this slot. And then you can also say where we have max flows in the. So of course we will have very high flows here around this here. This is also where we get erosion when you have groundwater flow. So that was the PowerPoint slide. So now I will try to switch to different one. Okay, so I'm back again with improvisation. So I'm running the first example here again. I have but I'm running it in the development environment. To find the points, we have an ellipse and splines, and then we have our mesh here. And we set an L size factor here. And then we create our mesh. And then we can draw the mesh here using chords, edof, dofs per node. So the same parameters that you have to tell the draw command what kind of mesh it is. We want it to be filled, and give it a title example. There's also a possibility to add text into this. This is not the purpose here. So if you run this now, yeah, it shows the images behind the window, which is kind of illogical here. So here you can see the generated mesh. And this is the geometry. So here I have used 4 node elements, so I can go in and change this. So I can change from element to type, I think it's 2 here, triangle, and if I run it again, we close these first. Now you can see here that we have triangle element instead. We can also control the appearance, how many triangles we want. So now you see here I have a scale element size factor of 0.05. Let's set it to 15 here. Or we change it back to number 3 here and we run. Now you can see here you have less elements because we reduced the restriction here so that you allowed for larger elements. And you can see here that the elements here are linear here, so we get this kind of jagged edge here. So this way you can change the element properties here. Then we take. Let's see. So in this example here, we have a. I'm just going to see if I can draw this for you. So this is an example here. We have a fixed wall here like this. We have something looks like, excuse my bad drawing here, dent defined by 2 curves, and we have forces here acting on the right side here. So we have defined a geometry something like this. And we go back here, same thing here, we use parameters, and that's my recommendation here to use parameters as often as you can so you can change the problem. So I collect all my parameters here in the beginning of my script. And yeah, and I use them later on. Then I create my geometry. This is a bit more complicated than before. And it loops and it creates a lot of circles and half circles and splines. And then we also put markers here to, here you can also see here, you put elements on curve here. That is a way of specifying the number of elements we need on a certain curve to kind of increase the precision. Then we specify the markers here for our boundary conditions, our arcs, and we create structure stuff. So this is quite more complicated problem. We have 4 node elements. This time we have 2 degrees of freedom per node. We create a mesh, and we solve a problem just like before. Create n dots, and we ex and ey, and then we create a loop for assembling the elements. We apply our boundary conditions here. So in this case, we have fixed at the marker 5, and here you can see I specify 0, 0 per 0 here. That it should be fixed, and the 0 here means that it should be fixed in all degrees of freedom, local degrees of freedom. I can specify 0, which is both, 1, which is x, and y, that is y is or 2 is y direction. And here we can apply a force to marker number 7. And we apply a force 10 raised to 10 e5, and then we have we apply it in x direction. We solve our system, extract element displacements, and we extract our element forces here at the end. Calculate from Mises. So you can get some hints here if you have solved the problem that the plate problem here. There is a lot of information here in the examples of CALFEM that you can use. So let's run this. And this is a structured mesh problem. So here you can see we build up our geometry using blocks here, or four-sided super elements, and we define here how many elements we need on each of these sides here. So this is a structured mesh generation. And then we can visualize element displacements. We can visualize effective Mises stresses inside the surface. And we can also just illustrate the mesh, generated mesh like this. So here you can see here that we have 10 here, and we have 10 here, but there are still blocks of regular structure superelements. So I think we take a 50 minutes break here, and I will discuss a little bit about how to set up your project with classes and mesh generation stuff after the break.
Excuse me, Yunus. I think you are muted.
Okay, let's see here. I'm not muted now. Good. So let's see here, go back to my. Okay, let's start again. So we start with the solver. It's kind of the central part of a finite element code. And we'll create a class for implementing the solver. So the code that you previously put into a single file will go into the solver, and we will implement a method called execute that will actually perform the solver, the solution of the problem. But to be able to calculate, we need to provide input. So we also create an input class, input data. which will be passed to the solver. The solver also needs the way to store the results. So we will create another class called output data. So when we create the solver instance, we will pass along as parameters to the constructor an input data object and an output data object. And you perhaps ask yourself, why do we need 3 objects for doing this? One reason for this is that it creates a very flexible architecture. You can, for example, create multiple objects here, input data, and loop over them. You can also, for every time you run a set of input data, you can store it in separate output data objects. So in this way, you can very easily create a lot of input data sets with where you can change the parameter, and then you can loop over them, and you can store. You switch out the output data object to a different one for each of these parameter steps. And the solver doesn't know anything. It has these objects, and it works on those objects for input and output. When we have a complete program, we also need a way to present our results or input and also the results in a nice report. So in that case, we also need to create a report class. And this report class, we connect our input data to, but we also connect our output data. And this class will generate an output here of a nice formatted report like this. And we don't have to give it anything else. We just pass along these output and input data objects, and they can create reports from those. And also the input data class can generate, can save its data to a JSON format. So you can read and write your input and open the file in the user interface later on. And then you have we will create your main window class here, where you have created a user interface, which we'll be talking about next lecture. And that will also have an access to the input data object. It will also control the solver that will control the output here. So from the main window or main program, we will create these different objects and pass them along inside a program. And that also makes it much more contained. You don't have a lot of variables spread out on the entire program. You have basically 2 objects that you manipulate, one input data and one output data, and then you pass them along to the solver, to the report, to the main window. You implement in the input data routine to save the file as well. So the JSON file will be our document format for this program. And just to illustrate a bit how this can look in code, I have looked at, this is the from your project here, from groundwater flow. So in this case, I have an input data class here with a constructor. I have created a geometry method here, which you also will create, that will be used by the solver we call geometry, and we'll get the defined geometry from the input data. So in the input data section here, you define all the parameters that define your model. And then in the geometry section, you will then create the required parameters here, or required geometry from those parameters in the model. So the solver will call this one. The solver will not go into and look at the parameter. It will just look at the geometry. And then we also have two methods here, save and load, that will save the input data to a file, and we've also been able to, you can read it back again from a file. Then we have the output data object, and its basic definition is quite clean. So the solver will actually create more variables inside this output data object. So we just created some placeholders for the displacements, for the reaction forces, for element displacement, and levels and stuff like that. So it will be empty from the beginning, but the solver will have the responsibility to fill this object with the results. And then we have our solver object. You see here that we give it input data and output data as input, and it will have those references internally when it does its calculation. There is an execute here, which will execute the calculation on the given input data. It will write the output data results to the output data structure. And further along in the course, you will also create a parameter study where we execute several calculations with varying parameters. Then we have the report. Same thing here, we give it input data and output data, those objects, and it will store those. And we will have an STR here that will produce the output report from the input data and from the output data. And I forgot, actually, we have a visualization object as well. So the visualization object also, we use the input data and output data again. We have a show for showing the windows. We have show geometry, show mesh. All these methods for visualizing the different results we want to show graphically by calling this method here. But you can see the information carrier is the input data and output data. You pass those along, solver will fill output data with data. You pass it along to report, which will print the results, pass it to the visualization, and which will then print and visualize the result with those objects. So if we look here, just not to expose everything here, we store input data as references here inside our objects as well. So we pass it along. So these variables here will be located in the main program. We pass them along and we store references to them inside our object as well, so that the visualization object knows which input data and output data to work on. Just to get so that you get a feeling of what kind of program this can be. Let's see here. So here I have main window class as well, but I will not describe it in detail here.
Is there any reason why we have the main window class within the main program instead of the flow model? Instead of in the flow model module? Yeah,
I have my principle is to always divide user interface code from the model code. Okay. But it could be, for example, you want to implement a web-based user interface for this. If you had mixed them, you have a main window in your web code, which you don't want. So that's why I try to create this model and a view. So that's why I separate this. Then you can change the user interface at any point to something else. So this is an example of how the code can look. So you have the parameters here. You can let's see here, just make it a bit bigger. So here you can see output from the report class. You can look at the, oh, couldn't. I'm not so lucky today. Okay, I put two small element size here. That's why it's a bit. And then you get your result windows here. So that's the idea of the program. So and the visualization module is responsible for showing this window here. And then you have the main window here that is specified for the user interface. And so on, and there's a parameter status. So this is the final result, so to speak. And that was actually all I had for today. So next Monday, I will go through how to create user interfaces. And it's good if you can be on Tuesday next week that you have completed the mesh generation part, so that you have a completed model. So when you go into the user interface parts, that your model parts are finished. That's important. I will also look into the Mac problems that you had. Any questions? It can be a lot of things to take in, but I hope I try to describe the overlay with the objects here, why we do the objects. And it's containers that you can pass along. Okay.